Okay, so here we are in the third and final part of the talk, in which I'm going to present a sketch of the proof of the main lemma that we use to prove our results regarding the Bernstein type problems for elliptic Weingarten surfaces. Okay, so the main lemma, if you remember, deals with not elliptic Weingarten surfaces, but surfaces with quasi-conformal Gauss map. So let me start by recalling some definitions and properties. So, well, quasi-conformal maps, or are also called sometimes quasi-regular maps, and they are a very well-known topic in analysis. But from our geometrical point of view, for a surface to have quasi-conformal Gauss map means that we have this inequality here between the principal curvatures of the surface. So this is equivalent to the fact that the Gauss map of a surface is quasi-conformal. And depending on this gamma, constant gamma here, this means that the curvature diagram of the surface, this is no longer a curve because it is not an elliptic and Weingarten surface. So the curvature diagram, the set of points in the plane where the principal curvatures live, is contained in either a wedge like this, placed here in the origin, or a double wedge like this, okay? And actually there is some connection sometimes between elliptic Weingarten surfaces of minimal type and quasi-conformal Gauss maps. And we have mentioned this in the first part of the talk. So for example, uniformly elliptic Weingarten surfaces of minimal type have quasi-conformal Gauss map. This is why the Bernstein problem for uniformly elliptic Weingarten surfaces is solved many years ago. And also, if the surface is not uniformly elliptic, but the principal curvatures are bounded, then the result is also true. It has quasi-conformal Gauss map. And finally, let me recall the result by Simon that we use in the first part of the talk, and we are going to use it here too. Simon proved that any entire graph with quasi-conformal Gauss map has to be a plane. And actually, the proof by Simon, although he stated it for entire graph, the proof works exactly the same for proper graphs. Okay, so it's a bit more general. Now, our main lemma says that if you have a complete multigraph with bounded second fundamental form and quasi-conformal Gauss map, then it has to be a plane. Okay, so to prove this lemma, reason by contradiction, and suppose that you have something that is not a plane, but is a complete multigraph with bounded second fundamental form and quasi-conformal Gauss map. Okay, so by Simon's theorem, your surface cannot be an entire graph because it has quasi-conformal Gauss map and it's not a plane. So, but your surface is a multigraph. So locally, around any point, the surface is a graph. Locally. So take any point of the surface, take the neighborhood around which the surface is a graph over some disk, this D here in the horizontal plane. And since your surface is not an entire graph, then there must be some point at the boundary of D. If you take the largest disk possible, there must be a point in the boundary of this disk at which the surface cannot be extended as a graph. Okay, so I'm going to label as Q this point at which the surface cannot be extended as a graph. Okay, so now the first step in the proof is to control the asymptotic behavior of my surface when we approach to this Q. And here we were inspired by an argument of Hosbury, Rosenberg, and Spruck for CMC surfaces in H2 cross R. But of course, we have to make some adjustments because we don't have a condition on the curvatures, but only that the Gauss map is quasi-conformal, this inequality that we have. Okay, so the idea is the following. Take a sequence of divergent disks in the surface as you are approaching to this Q. Okay, so this is the piece of your surface that is a graph and cannot be extended to Q as a graph. So take a divergent sequence of disks and up to a translation to the origin, what you can prove is that since you have bounded second fundamental form, this means that the functions that define these graphs are bounded up to the second derivatives. So you have convergence of this sequence in the C1 alpha topology, okay? So this divergent sequence of disks up to the translation, to the origin, actually converges to limit surface, C1 alpha, limit surface, okay? Now, all the red surfaces have a quasi-conformal Gauss maps because they are part of my original surface. And because of the properties of quasi-conformal maps, if you have a sequence of quasi-conformal maps, you can prove that in our case, the limit is also quasi-conformal. So you have a limit surface with quasi-conformal Gauss map, but the Gauss map of the limit surface is not open. This is because on each red disk here, the Gauss map takes values in an open hemisphere because this is a graph. So in the limit Gauss map will take values in the closed hemisphere, but it actually takes values in the boundary of the hemisphere because as you approach to this point Q, the tangent planes are becoming vertical. So the Gauss map are becoming horizontal. So in the limit, your Gauss map is horizontal. So it takes values in the boundary of the hemisphere. So it is not an open map. And if a quasi-conformal map is not open, then it has to be constant. So the limit surface has constant Gauss map. This means that the limit surface is a plane, okay? Great. So this is another picture of the same situation. We have a piece of our surface that is a graph over this disk, but there is a point Q here in the boundary of the disk at which the surface cannot be extended as a graph. And what we have proved is that at this point, the surface becomes asymptotic to a vertical plane. And not only this, but we actually can prove that the surface can be extended to a graph over this some region like this here, some neighborhood, as the orange one, and it is asymptotic to the vertical plane as you approach or to this line here, okay? And this happens every time that you have a point for which the surface cannot be extended as a graph. What happens if I have another point like this? Well, if you have another point like this and is placed like this, for example, then the asymptotic behavior is the same one around this point. So, but this gives you a contradiction because around these points here, on the one hand, you have to be asymptotic to this vertical plane here, but on the other hand, you have to be asymptotic to this vertical plane here. So this is impossible to have something like this. So the only possibility is that if you have another problematic point at which the surface cannot be extended as a graph, then it has to be like this, an antipodal point. And in this case, what you actually have is that your surface is a graph over a band and is asymptotic to these vertical planes here. And the other possibility, of course, is that you don't have any other problematic point. You only have one. So if you only have one, then what you get is that your surface can be extended to a graph over a half plane and is asymptotic to this vertical plane here. So at the end, what you prove is that your surface is actually a graph over some, or a band or a half plane. So it is a proper graph in R3 with quasi-conformal Gauss map, and it's not planar. So, and this is a contradiction with Simon's theorem. So this finishes the proof, okay? So once we have proved this main lemma, we have all these three results that we saw in the second part of the talk regarding the partial resolution of the Bernstein problem and generalized Bernstein problem for elliptic Weingarten surfaces. So that's all. Thank you very much for the attention. I hope you enjoyed the talk. And Bye-bye. Thank you very much.